Hello and welcome back. I wanted to make this video as a standalone. It's going to be a quick one, just going over some of the basic properties of the dot product. This way you can come back to this video if you need to, and it's just standalone by itself. So three sort of main properties, algebraic properties of the dot product. One is that it's commutative. That is, u dot v is equal to v dot u. Now this can be easily proved, or just seen, by using the geometric expression for the dot product. That is, we know that u dot v is equal to magnitude u times magnitude v times the angle between them. The interesting thing here is that the angle between them does not change if I change the order of them. So v dot u is also magnitude u times magnitude v times the angle between them, which is the same. And so they're exactly the same thing, just establishes that this product is commutative. Another fact here is that C, if I scale a dot product, so I'm not actually scaling a dot product. What this multiplication is the multiplication of two real numbers, right? U dot v is a scalar, and C is a scalar. So I'm just taking, this is just normal multiplication of real numbers. This is the same as if I scale u, so this is scalar multiplication, so a scalar multiplying a vector, multiplication, dotted with v. So this is now a vector, right? V is a vector, and if I take the dot product, I end up with a scalar. So this is another way to do this. I can either do multiplication between scalars, or I can scale a vector and then take a dot product. I end up with the same thing either way. This is, one easy way to see this is with the more algebraic or arithmetic notion of the dot product, or expression for the dot product. And that's, right, so if so here we would let u be u1, u2, u3, and v equal v1, v2, v3. I can compute the left-hand side. So this is how we establish an identity like this. We can compute the left-hand side. So 1 u dot v, we know, is u1 times v1 plus u2 times v2 plus u3 times v3. And so if I take c, this real number, and multiply it by that, well, that's going to be c times u dot v is c times this whole expression. And I can bring that c through to each one of these. So now I'm using the distributive property of real number multiplication, u2 v2 plus c times u3 v3. And now I'm going to use associativity of real number multiplication. So this is c times u1 times v1 plus c times u2. So I'm just thinking of doing that operation first, plus c times u3 times v3. And that is the same then as if I scale c, or if I scale u, right, I'll get cu1, cu2. So let me maybe write that up here. So c times the vector u is cu1, cu2, cu3. And then if I take a dot product of this with v, I get exactly what I have up here. And so that's cu dot v. That establishes this property of dot products with scalar multiplication involved. Last one is this distributive property of dot products. I'm going to keep this video as short as I can, so I'm not going to run through the proof of this. In fact, that would be a great exercise for you to do, is to run through a proof of this one. Use the algebraic or arithmetic version of the dot product, and this will pop out. And use the component version of vector addition to get this, then take a dot product, and you'll recover this one. That's a nice exercise. I encourage you to do that yourself and prove something yourself. That'll be very meaningful for you. So these three properties of the dot product are important to keep in mind.